uh, building blocks are building block properties are essentially decoupled in nature, they are independent. Okay, let's talk about uh, first how to model a simple spring mass damper system. So in general, the elongation of any rod, or if you have a house, columns, beams, you can model those columns or beams through the simple spring damper or dashpot and the mass. So in order to analyze this system, we need to first draw the free body diagram. Or the FBD of the system. So let's suppose so this is your axis system and this is your x coordinate. Whenever I apply a force F to this mass M, the spring stretches x displacement, and that at that moment, let's suppose I have x dot velocity of this mass. So what happens? So let's suppose this is your point mass M, and you are giving a force F, external force F in this direction. This mass will experience a left side force F spring is equal to k times x displacement, and also it will also encounter a resistive force due to the dashpot Fd or damping force, which is equal to c times x dot. Now I can do the force equilibrium. So if the system is in equilibrium, and so because of this external force, you will have an acceleration in this direction. You get an acceleration in this direction, right? So I can write F external is equal to ma, Newton's law. So what is this F? F I can write F spring plus F damper is equal to m times d d2x by dt square. F spring I can write kx plus c x dot dx by dt. So this is this is my F net. Your net force will allow your mass times acceleration. So here this is my F external minus of these two forces. F external minus of these two forces will tell me the required acceleration, right? So basically Newton's law says that total force external summation of all those forces will lead to mass times acceleration. Okay, so I can write F is equal to m d2x by dt square plus c times dx by dt plus kx. So this is your mathematical representation of this simple block, and this simple block can be seen in your very real life examples such as bending of rod, lengthening of rod, column, beams, your aircraft, anything. So essentially this is your input to the system. You are inputting this F force, and this X is your output. Either it could be X or X dot or X double dot. It's up to you, but in general I'm interested in looking the displacement of the system, right? How much it displaced with this force. Okay, so essentially it is a function of time. So this the solution of this x dot and x, the solution xt can be obtained through the dynamic analysis, which we are going to learn in this chapter, dynamic response of the system, in the next chapter. And how we are going to do, we will take a help of this transfer function analysis, which will ease my life to obtain the solution of the system, because currently you cannot solve this system, this particular system, because it is complex to solve. But when we apply the transfer function analysis, you will see in subsequent chapter, transfer function analysis, your life will be easy. You'll easily get the solution xt as a function of time, and you can analyze that the system very easily. Okay, let's take another example, slightly complex example. Let's take one example and then we'll see, or maybe first what we'll do, we'll take some real life examples, such as your car. Let's suppose you have a car, you have tires, and so this, you have a tire, you have a chassis, and you have a person sitting on the this is your chair. So your driver or a chair will act as a mass, and we are looking into the y-axis response of the system. So your chair is connected to your chassis with spring and dashpot arrangement, so to say. So all this system can be well characterized by assuming that car and chair are connected through this spring and dashpot, and the chassis is connected with the suspension of the car, again with some other dashpot and spring of the system. Suspension system, and then your tire will act as a spring only, and this is your ground. So this whole setup is your car, and if you have a bump, let's suppose you are oscillating this ground by some x with respect to time, how your car x car will behave with respect to time. So what is the good about this study? So we can analyze, or we can design this spring and dashboards in such a way that even if you have a very large bumper, your car response will have a comfortable, your car response give you a comfortable ride. Right. So that is why we want to seek the solution of this, the behavior of this X car or the chair, so that you have a comfortable ride. There are all sorts of examples. Okay, let's look into the example. So in this example, let's suppose I have two springs. This is my K2. Let's suppose this is my mass M2. It is all again connected with another spring K1 with another mass M1. When if we apply an external force F on mass 1, and we want to obtain, so this is your x1 displacement and this is your x2 displacement of this mass. These are absolute displacements. Okay, you will fix your coordinate here and let mass move in this direction, absolute to these axes. So obtained x1t and x2t. This is my claim. I want to seek these displacements with respect to time. So let's write a free body diagram. FBD first. So FBD of this mass 1, let's suppose mass 1, I want to seek the FBD first. So this is your external force F. The spring K1 will be stretched x1 amount, right? So it will be pulling with this K1 x1 force only, and it will give you an acceleration x1 double dot. Whereas if you talk about M2, what are the forces? Right side will have a spring force, okay, I did a mistake here, sorry. So this K1 x1 will not be the spring force. What would be the spring force here? So this is absolutely going x1 in this direction, and this is going absolutely x2 in this direction. So the net extension in this K1 spring is basically x1 minus x2 if x1 is greater than x2. Let's suppose I also assume my x1 is greater than x2, right? Then the displacement in this spring is x1 minus x2. So this spring force is now K1 times x1 minus x2, right? Now let's talk about the forces on this mass M2. So this is the extension is in right hand side, the spring has same extension, so it will pull in the same fashion, k1 x1 minus x2, and the left spring k2 has absolutely moved only x2, right, and it will give me its acceleration absolutely x2 double dot. So when I am writing the equation of motion here, I will write F is equal to